So let's look at an example, and I must admit it's an easy example. It's an example to exemplify again the beauty of the triangular form. Because you see, this matrix is in triangular form. So if I look at the eigenvalue equation, we know that this matrix here has to have a vanishing determinant. So I will write down this matrix, which means I will subtract the lambda in the diagonal and then have a look at the determinant of this matrix. So our characteristic polynomial, the determinant has to be 0. And if I calculate this determinant, the beauty is that, of course, I only have to now multiply the diagonal elements. And my polynomial is already factorized. I already know the solutions for lambda. One solution is 1. This term becomes 0. One solution is 2. And one solution is -1. And all of my eigenvalues are different, so I will expect that I can easily calculate the eigenvalues for that. So now that we know the eigenvalues, we can have a look at the eigenvectors. And for each eigenvalue, we will get one eigenvector. So let's try to find out μ1. So I take the eigenvalue equation again. And this transforms into where you can see the fact that it's a linear equation system. If I take the last row, what I get here is 0, 0, minus 2 mu z is equal to 0. From that, I can easily see that mu z is 0. From the second row, I see that 0, 0, 1 times mu y is 0. The only term that's not 0 will be here, because here I have 0 times mu x, which is 0, 1 times mu y, which is 0, and 1 times 0. So here I have 0 is equal to 0. Here my mu x is my free parameter, and the solution in the end for this first eigenvector will be either mu x 0, 0, and mu x is your degree of freedom, or if you want to normalize the vector and you want to keep the length separate, you can write it like this. Length of vector mu1 is unknown and the direction is 1, 0, 0. Now I will repeat this for the second eigenvalue, not for the third. The third will be too easy, and I hope that the principle is clear after this one already. So let's look at the second eigenvalue, and we look for the second eigenvector. If I subtract this from the diagonal element of my matrix, I get and again, 3 equations, 3 unknowns, I can solve this. Let's look at the last row, because it's the simplest row. Minus 3 times mu z is equal to 0, means mu z is equal to 0. Let's look at the second row. Mu y, I can't say anything about this. This is 0 is equal to 0. So let's look at the first row. Here I have minus mu x plus mu y plus mu z is equal to 0. Okay, if I look at the mu z, that's 0. So this equation just means mu x is equal to mu y, and mu y is free to choose. This then now means for the solution that either I put in the same coefficients in the x and y position, or I take out the length again and have the vector 1, 1, 0. Here you see I've chosen easy coefficients. If I now want to normalize this, I have to choose mu2 here, the length, as 1 over square root of 2. Then overall this vector would be normalized. That's again up to you or up to the explicit question that you've been given.